Hello everyone, my name is Maciej Godek and I'm going to talk about the culture of scheme programming, and I will begin with a small question. Does anyone of you here have any experience with programming in Scheme? I see no hands, so I assume that no, but I will try to prove to you that it is a lie and you actually all have. So I will begin as a philosopher. I will begin with a philosophical question: what is a computer program? And well, I would appreciate if you try to come up with some of your answers. But well, I have mine prepared as well. So I don't. Well, even if you remain mute, the show will go on. So. Anybody has an idea what a computer program might be? Okay, so we could say that it is a set of instructions for a computer to execute under some specified circumstances. And if we follow that mental path, then we will reach the following implications. That first, well, programming is about instructing computer how to perform a computation, and this is how we might approach to software development. So we like have some problem to solve. We come up with an idea, then we have another problem to solve. We have another idea, like we write a procedure, a program that does something, and then we observe it that there is like that there are some similarities. We see that there are certain patterns that emerge, and this is how we grasp like some sort of unity within computer programs. And
there is some kind of echo. I don't know if it's from your PC or from we hear you from your PC also.
Mm-hmm. Okay, I mean that's. So, is it good or is it bad?
I don't know if it will not be strange for others. I don't know if it will be some kind of loop. Maybe from the stream, people who are seeing us will hear us.
Okay, but I don't know if I can do actually anything about it. So software developers, they form some sort of principles, like that there should be a dry spot, that you should not repeat yourself. Dry stands for don't repeat yourself. Spot stands for single point of truth. And software developers keep writing code. So they and typically in this metaphor, wet stands for write everything twice, or we enjoy typing, or write everything 10,000 times. And well, I don't think this is a good approach. I mean, it's like we're doing a big mess and then we try to clean it up. So maybe we could come up with some other idea on what a computer program might be. And I would say that it is a way of expressing ideas or communicating them to other people. And well, I don't think that it is a rare view nowadays, but this inevitably leads to a question: what is an idea? Does anybody have an idea about that? I've been thinking a lot, and I didn't come up with anything great. So we could trace the origins of this word. It comes from ancient Greek "idein," which means to see, or eidos, which meant for the Aristotle the essence, or the thing that makes a thing the thing. So maybe if we cannot formulate the definition of an idea, we could just there is a Greek mathematician, Euclid, who was thinking about what is a point, and he eventually conceived axiomatic methods of reasoning. And maybe instead of asking what is an idea, we could ask what can we do with ideas. So we could know how they operate in the system of science. So We could ask philosophers what do they think, and John Locke wrote in his essay concerning human understanding in 1690 that the acts of mind are chiefly these three, combining several simple ideas into one compound one, and thus all complex ideas are made, bringing two ideas, whether simple or complex, together without uniting them into one, by which it gets all its ideas of relations, and separating them from all other ideas that accompany them in their real existence. This is called abstraction, and thus all its general ideas are made. I have not a clue what this might mean, especially the ideas of relations. So, but maybe we could get an inspiration and define idea like, we could enumerate some, like, any general idea is some sort of either a simple idea, or it is a complex idea which is made by combining simple ideas or simpler ideas. And we could also have some combination and abstract from it. And that's how we might conceive ideas. So another question that we might ask is, well, I didn't expect this slide to come up here, but we can ask, what does it mean to understand an idea? Well, if the complex ideas are composed from simpler ones, then we can reduce a complex idea to simpler ones so that the simple ideas are obvious for us. And we also understand ideas when we are able to map ideas onto our experience, or we can like do some sort of mental movements with these ideas. And that we are able to draw some practical conclusions and apply the ideas to our own existential situations. I think that would be the just, I don't know, the just answer to this question. Well, what does it have to do with programming? Well, there are certain, I mean, I will try to show more during this presentation, but we could say that, I mean, Kristen Nygaard, the Norwegian computer scientist, said that programming is understanding, and Alan Pellis said that you know when you can learn, are more sure when you can write, even more when you can teach, but certain when you can program. So I think there is a very narrow distance between programming and understanding. I mean, of course, someone who doesn't do any programming can say that it's, well, it's obviously not true because I don't program and I understand things, but I think that is a good practical criterion for saying whether or not we understand something. Okay, so now here's the question, why do we need ideas? I think it's a very strange question. I mean, when I wrote it, I think there's something puzzling. I mean, it is so obvious that we need ideas to like navigate around the reality that well, it's even strange to ask such question. But we could make a bit more specific question: why do we need complex ideas? And I think it is a better one. And but I don't know. Maybe you have the answer to this question. Why might we be needing complex ideas?
Usually when we code, when we program something, we try to program something which is in reality, and reality in itself is very complex.
So okay, so the answer is
maybe it comes simply from requirements.
from requirements.
Yeah.
Okay, so the life requires us because reality is complex, and we are trying to reflect the reality, or we try to do something in this reality. So we have to make our minds or our ideas more complex. Yeah, fair enough. And now here's a simple one. What are the means by which we create new ideas? It's very simple. It's tricky. I've already shown it. I mean, an example of this means before. Dun, 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 dun. It's a definition. This is a definition of a definition. So it's a linguistic expression whose purpose is to introduce a new term based on some terms that are already known. And when we take a look at this definition, we can distinguish that it has two parts that are traditionally called definiendum and definiens from Latin. So the definiendum, the term being defined, and definiens, so to speak, conceptual content of this definition. And when we take a look at this definiens, we can, in many cases, not in every case, we can distinguish two parts: a genus or some like category to which a defined term belongs, and a differentia, and the difference, that's something that makes it distinguished from that category. This is, I think, Aristotle called, or logicians call it, normal forms of definition. Previously, when I've shown definition of an idea, it was different. It was inductive, because we said idea is one of the simple ideas, or it is something composed of some other ideas. I think that functional programmers are in particular familiar with this kind of idea. So here's a little bit more complex definition. I think some of you may recognize what that is. Well, it is a Turing machine, and I think it gives a good clue why definitions are useful to us, because, well, after, because, well, how to say it? Alan Turing, having formed this definition, he actually created some new branches of science. He gave us a new aspect on what humans are. I mean, after winning the World War II, Alan Turing, well, he didn't ask, how can I apply this Turing machine to bring me more revenue on my new e-commerce platform that I could expand on new markets? But instead, he said, can this think? I mean, can a machine think? Or what is it so special about humans that they are able to think? Thanks to this very definition, we now have like whole branches, new branches of sciences, like cognitive sciences, that we are trying to describe our minds as if it were computers. Here's an idea from the philosophy regarding the composition of ideas. It is called the principle of compositionality, and it is attributed to Gottlob Frege, although I don't think he was actually the first to propose it, that the meaning of a complex expression is determined by the meanings of its constituent expressions and the rules used to combine them. And so I think it gives a clue to us how we can understand things. We can simply decompose them. Also, this is my hypothesis, that if you have a complex expression, you can distinguish a ruling word which determines the meaning of the whole expression. So, like there is for every expression, you can have a hierarchy of, you can have this distinguished element that you can call the ruling one, and some subordinate expressions. And as a conclusion, we can build, we can represent expressions that denote some complex ideas. We can represent them as trees. In other words, we could say that languages have syntactic and semantic structures. I mean, syntactic because this is a syntactic object, but we would like to believe that it has a corresponding semantic object. That there is for instance, there is a number in some Platonic world to which this complex idea refers. As a philosopher, I could not resist the temptation of asking myself the question who we are. In the face of this presentation, And Aristotle defined humans as zoon, logon, echon, or an animal in which the logos echoes, or it is sometimes translated to Latin as anima rationale, a reasonable animal. But it's not about reason, it's not about, because logos means different things in Greek. It means logos, it means language, and it means reason or thinking. And if we take a look at some texts that are essential to our culture, we inevitably run into this quote: "And out of the ground the Lord God formed every beast on the field and every fowl of the air, and brought them unto Adam to see what he would call them. And whatsoever Adam called every little living creature, this was the name of thereof." So actually naming is very essential to our existence. And it forms our nature. And we could also ask, well, what is the relation between language and cognition? Ludwig Wittgenstein, Austrian philosopher, said that the limits of my language mean the limits of my world. So it may be an interesting question, well, to look at those limits of your language. And there's this rather lengthy quote from Benjamin Worf, who is famous for formulating Sapir-Whorf thesis that the language gives us categories in which we perceive the world. This is called linguistic relativism. And another question that we might ask is, how is communication possible? I mean, how is it that I speak some sentence and there's another person who I believe knows what I mean? I mean, and I sometimes hear people saying that that everything is relative. I mean, that it is up to someone's interpretation, that I can understand words differently than somebody else. But, well, this view, it should be called idios logos. These funny Greek letters can be read idios kosmos, which means private world, but there's also this hypothesis of private language that we use to think, because I think it is a common view that that we use language to communicate and to think, and we can grow in ourselves our inner language that facilitates our thinking, but we also need to communicate. By the way, this word idios, it means private, but it also means domestic or house steady or something like that, and actually it is the origin of the word idiot, because for the ancient Greeks, an idiot was someone who had his private language, who didn't use it to communicate, like Humpty Dumpty from Through the Looking Glass, from the story of Lewis Carroll about Alice. When I use a word, Humpty Dumpty said in a rather scornful tone, it means just what I choose it to mean, neither more nor less. And the opposite of this view is the koinos logos or koinos cosmos, that there is a public world. And actually, if we don't want to be, this is a straightforward conclusion, if we don't want to be idiots, we have to make our code open source. So since this talk I started as is about communicating ideas, maybe we could perhaps use our natural language that we speak every day to communicate ideas. And this is obvious because we actually do it, but it has its limits, because as you may see, natural language is susceptible to ambiguity, like in phrases, prostitutes appeal to Pope, or Reagan wins on budget, but more lies ahead, or Soviet Virgin lands short of goal again. And another problem with natural language is that it is, I mean, it depends on how you use it, but it allows its users to use it very freely, and it may sometimes be an obstacle for communication. This is a quote from Esker Dijkstra, who wrote a text on foolishness of natural language programming, that I suspect that machines to be programmed in our native tongues, be it Dutch, English, American, French, German, or Swahili, are as damn difficult to make as they would be to use. And here's a contrary view. I mean, this is actually a computer program that makes a solution to a Hanoi Tower. I'm sorry for the font being so small, but I just tried to fit it. It is written in a programming language Inform 7, which was created for writing text adventures, text computer games that you can interact with using text. And it actually runs. I mean, I didn't run it, but it allegedly actually runs. Okay, so another undesired trait of natural language, it's verbosity. And actually, this is why mathematicians come up with their notations that are brief. As Alfred North Whitehead wrote, by relieving the brain of all unnecessary work, a good notation sets it free to concentrate on more advanced problems and in effect increases the mental power of the race. I got this from some book. In the 12th century, the Hindu mathematician Bhaskara said, the root of the quotient of the greater irrational divided by the lesser one being increased by 1, the sum being squared and multiplied by the smaller irrational quantity is the sum of the 2 third roots. Are you still listening to me? Because I stopped listening to myself, but because it's very obscure. But when you look at this mathematical formula, of course, after some training, you see that this is obvious and this is not. So maybe we should pursue that idea and focus on using the language of mathematics to express ideas, because it offers us compact notation. And if we wanted to use mathematics to write programs, we can look at them from the perspective of their algebraic properties. And this is something that actually has been explored in languages such as Haskell or John Bacchus's FFP. But the problem with mathematicians is that they like to use funny symbols, and in some narrow context, these symbols may be fine, but they do not scale properly, and it's better to use words as we do in the natural language. So now I think, because I believe that you are experts on functional programming, what is so great about functional programming?
Hipster points.
Pardon?
Makes you very cool at conferences.
Well, I never thought about this, but now that you're talking about it, then I guess it's right, and maybe some other points.
Is there a reason about no type errors?
Yes, these are the buzzwords of functional programming. Yes, and testing. I forgot the testing part, but oh.
You have cursor on the.
Oh, okay. Okay, so we begin again. La, 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 la. I will try to keep the cursor far away. Okay, so here's the answer. I mean, you can have all the fun and no side effects. I don't know. When I first saw this picture, I was wondering how do the teenager knows what a comonad is. But this is the fact that when you are not careful, if you assign your variables, then you might end up with a mutating state. So maybe there's something deeper in functional programming. That it's again a biblical quote. In the beginning there was a word, and the word was within God, and the word was God. So what is so special about words? How would you define a word? What is distinctive trait? words refer to things. I think this is essential, that we have these two universes of word and universes of things, and that when we talk about the world, or when we talk about anything, we are not destructive. When we are making a SQL query, if it contains no update and no remove, if we perform a pure select, then we do no harm to the system. So in this respect, functional programming is just like speaking a language, but the language is much more condensed. And you cannot say this about imperative programming languages because, because I think that trying to speak imperative programming language would be like trying to instruct your brain how to decode the words that you are just saying. And now, after this introduction, an intermission. Because I've used some biblical quotes. Here's a quote for, what's the word? Przeciwwaga. Never mind. For the balance. Yes, counterweight. I hope the field of computer science never loses its sense of fun. Above all, I hope we don't become missionaries. I don't feel as if you were a Bible salesman. The world has too many of those already. And this is from the Foreword of Structure and Interpretation of Computer Programs, the Bible, the real Bible of functional programming. I think it's actually the New Testament, because the Old Testament is Donald Knuth's Art of Computer Programming. Anybody knows this book? No? Yeah. It's available free online, so you may want to check it out. And now we begin with the main part of this talk, which is the culture of scheme programming. And we will begin with some assumptions. Antoine de Saint-Exupéry wrote that perfection is finally attained not when there is no longer anything to add, but when there is no longer anything to take away. And similarly, the report on the algorithmic language scheme claims that programming languages should be designed not by piling a feature on top of feature, but by removing weaknesses and restrictions that make additional features appear necessary. So in this context of this very minimalistic philosophy, we may ask, what are the necessary components of an expressive programming language? And we recall the principle of compositionality, that the meaning of a complex expression is determined by the meanings of its constituent expressions and the rules used to combine them. So maybe we could just try to come up with the simplest conventions that we could to get a programming language. So, for example, if there's one distinguished ruling word that is crucial for the meaning of the whole expression, maybe we could just write it first and then write the constituent expressions to the right of the ruling word, because we're living in the Western civilization where we tend to write things from left to right, or where the time passes from left to right. And we surround this combination in parentheses, et voilà. So, for example, the example of the expression that I gave before would look like this in our notation. And we may also note that this guy in here is more versatile, because you don't necessarily have to put words in here. You can put other trees, so to speak, or other complex expressions. And now a quiz. Which syntax is better? Jak powiedzieć po angielsku? Pytania są tendencyjne. So, okay. So the questions are suggestive. Which? The one on the left, hands up. The one on the right, hands up. Okay. So one hand is up, and you were all right. I mean, None of them, because it's actually very accidental whether you use C syntax or Pascal syntax or Scala syntax or actually any other syntax other than I just presented to you, because of the trait of homoiconicity. So what is homoiconicity? It is not something that you might have thought about. It's the property that the language that you are using to write, you can look at this language, look at the expressions that you wrote, and perceive them just as a data structure to your program. So you can easily write programs that modify your programs, and this is the syntactic basis of scheme. And now for the semantics, the lambda calculus. It is good. I mean, it is valuable. It makes things easy to reason about because of the thing known as substitution model of computation, that you can look at the evaluation of a program as transformation. You simply have a text and it gets transformed to some other text. So this is the basic principle of lambda calculus. It is actually very simple. You have a lambda of some argument, and the argument appears somewhere in the body, and you can apply this lambda expression to some argument, and you substitute the occurrence of the variable of x with the thing that you supplied to it. So it's just that simple, and it is equivalent to the Turing machine that I've just shown you a few slides before. And it actually does a little bit more than just pure lambda calculus, because it allows assignments, and it defines applicative order of evaluation, whatever that means, never mind. And this is actually the core language scheme. It provides us with a means to define new notions. It provides us with a means to abstract from combinations. It also has a conditional clause. It has a clause that exploits its amazing possibility to this property of homoiconicity. It's got the infamous assignment, and this is actually just like nothing important. And another thing, control structures. Anybody knows what goto is for? It's for jumping around the program in non-structured programming. And break is used like in languages like C, continue, return, throw, catch, yield. These are all some different sorts of control structures, and Scheme has none of them. It has a control structure or pseudo function called with current continuation. If you're interested, I could show you one day how it works, but you can define each of those previously mentioned structures using this one, and some macros probably, some sort of syntactic extension. And another thing that is very important in for schemers is the self-describability. So the structure and interpretation of computer programs, the book that I mentioned before, it claims that the evaluator which determines the meaning of expressions is a programming language just as, the evaluator which determines the meaning of expressions in a programming language is just another program. So basically SICP claims that this is the most fundamental idea of programming, and everybody who has had any experience with writing compilers or interpreters knows that it's just true. That, well, it's the programming language that you use to describe a programming language. And of course, you could also use a natural language, but there's an interesting idea there that you can try to express the meaning of a programming language within that programming language, and this is called the metacircular evaluator. So now another quiz. Which notation is better? Underscore notation or camel case notation? Well, I see no hands. So, well, I claim that this is better. I mean, European typography just doesn't contain these characters, and it doesn't do things like that. I mean, before the programming books appeared, I don't think that any typesetter would ever think about anything like this. And well, why do we in the Lisp communities nobody uses anything like this because they've got this, and I think the reason, well, is that the designers of most programming languages were too frightful to not to distinguish the algebraic operator of subtraction. But actually, how often do you use subtraction in your programs? Not very often. And how often do you come up with the names for notions in your programs? I think much more often. Okay, so another quiz. The person who answered was what this program does gets a free beer. So it's worth battling. Any ideas?
Hello.
No, not even close. I mean, slightly close. It's a functional programmer's hello world. It's a program that computes factorial. And it's actually, I think that this is a minimalism that got wrong because it didn't provide any means of defining new notions. So you just had to put all the combiners together. And now I have because I've just shown some design principles of the scheme programming languages, and now I wanted to show you the fruits of it. And there's a YouTube video, but I don't know if it's going to work. It's going to only last a minute, if it will. Am I going to screw the streaming right now? This is also an interesting question. Okay. Okay, this is a 3 years ago news, but there's no voice, so hold on, I'll just have to
Display. Are you connected to HDMI?
Okay, you may check it out.
I was told it should work, but no.
Okay.
Know the password.
Oh, well, there's some voice.
Impressive skills that have earned the respect
I'll
of the next
rewind.
Bill Gates or Steve Jobs, maybe a little girl from West Philadelphia. She's got some pretty impressive skills that have earned the respect of some huge celebrities. Fox 29's Stephanie Esposito introduces us to this young tech wizard.
Zora Ball is 7 years old. She's a ballerina, likes to get her nails done, and
It says, okay,
See,
what?
parentheses.
she's the youngest person to ever code a video game. What does minus y20 mean?
20 means the speed.
The West Philadelphia first grader was introduced to a program called Bootstrap by one of her teachers at the Harambe Charter School.
Again, just wanted to push the envelope and do something different, and then really just see if she could actually grasp the concept.
I had to do a lot of math.
Zora joined a Saturday class with 5th and 6th graders. Her teacher, Baba Tariq Nazir, taught them a very simplified way to code. After 10 weeks
Okay, so this is the very simplified way to code according to the television. I mean, this is not like it's not the MIT Scratch language where you like put some control structures on the screen and play it with as if they were building blocks. You actually use some real programming language that the television, I think it's a world's conspiracy, that the television calls simplified programming language. But I'm really proud to be a part of community that produced or celebrates this invention. Okay, so now another fruit apart from 7-year-old girls who program computer games. Another fruits of the scheme's simplicity is is that there's many implementations, and these are actually really good ones. There's a recently released to the open source chess scheme, which, well, it's probably one of the best compilers in the world. There's a racket which has been used in this course, Bootstrap, and it's very good for education. It comes with a very nice IDE and some cool stuff, like you can assign meanings to images, for instance. There's this Kava or Kawa scheme, which was it runs in JVM. I think its performance is comparable to Scala. And well, I'm talking about it mainly because Per Bothner, its author, he is also the author of GNU Java compiler, and he said, well, there's really great piece of software that is not really well known. There is a Gambit, a compiler that compiles Scheme to portable C code, and it comes with an interesting framework, Termite, which is similar to Erlang, if anyone knows what I'm talking about. My favorite implementation is called Guile, and it was initially intended as an extension language for GNU projects to embed, and there's Biva scheme, which is an interpreter written in JavaScript. You can run it from your browser, and there's Iron scheme that runs on .NET framework, and there's approximately 80 other implementations. Some of them are better, some of them are worse, but they are actually rather good quality. Since Scheme is so simple, you can easily define macros. So, for example, if you are familiar with the let form from other programming languages, here's a let form that assigns name to binds name with a value and evaluates an inner expression, and it can be defined in terms of lambda. And this explanation that I've just told you is well, when you put it around some abracadabra, it becomes a legitimate part of your language. So I think that this macro system is, it might be quite impressive at a time. Another thing that is really cool, I really like it, is that you can comment out nested expressions. I think that, well, I know that Clojure is built on the same principles as Scheme, so it's no wonder. If you haven't worked with environments like Geyser or Enclosure, that's I think they got Figwheel and Cider inside Emacs. You can write your program and evaluate it at the time of writing, and this is really like very comfortable approach to programming. And well, thanks to the simplicity of Scheme, you can even overwrite core bindings. So if you don't like the language that you are using to program, you can define your own. So this is an example of carried definitions that you may want this definition, this definiendum, to expand to something like that. So f is a function that takes an argument and returns a function that takes an argument and evaluates body. Another thing that I added, because Scheme didn't have this originally, I could add pattern matching to the core lambdas. I could define my own like core binding and pretend that it's the original one. So I could define some quite useful syntactic extensions or syntactic abuses to be valid. And I think Scheme prompted some of ideas that are unthinkable, that would be unthinkable in other languages. I don't know if you know the work by Daniel Friedman and William Bird. They've been last year in Poznań. Will Bird has been showing this. It's running evaluator backwards. You can type the value of expression, and it generates for you a list of programs that evaluate this expression. So it's quite fertile. There's also it's an idea from Daniel Friedman, the idea of ferns, and lazy streams actually. They are very popular now. They originated in the 70s, and one of their inventors was Daniel Friedman, who wrote a paper, "Cons should not evaluate its arguments." And there was just a tiny tweak in the semantics of the list constructor that allowed to build like infinite lists. You probably know. Okay, so this is a programming trick that I came up with, how to memorize the order of arguments to a function. You could use the fact that you've got this one expression comments, and this code, it is not very important. I just gave it as an example. This is a solution to traveling salesman problem based on Held-Bellman-Karp algorithm. It defines a shortest cycle from first like city or whatever point of a graph through rest. So you can read this code rather smoothly. Shortest path from node to target through other nodes. You can. I think I don't know. Do you like it or not? But I think it makes working with the code much smoother, and it makes it more clear what are the roles of arguments. And this is another idea that I've had. I've been writing chess program, and I thought how to describe chess, the rules of chess, to a computer in a way that would be understandable for humans as well, or how would I understand the rules of chess to humans? And I came up with this notation. You've got these dots, but I think the picture should be rather clear, that if you have this situation, that you have a bishop and an empty field many times repeated, and you have opponent or empty field, then you can move your bishop there. And this works in all directions. Okay, so another idea that I've had, thanks to the use of macros, is to embed tests in between the definitions. So, for example, if you were supposed to guess what this program means, what this function does, then, well, you would have to analyze, and it's not as straightforward. But if you take a look at this example, I think it becomes clear, like that you take 3 elements of width and 2 elements of height from the upper left corner. And this is not just an example that is ignored, but it also works as a unit test. And I think because Scheme is not a purely functional programming language, unlike Haskell, but I think it can still have, the programs that are not pure can still be perceived or analyzed by interesting means. I mean, this is a part of a program that I wrote for genetic programming, where daddy and mommy are chromosomes. So there are lists of Boolean variables, and they are of equal length as this assertion claims. And we pick a random position that is between 0 and the length of daddy minus 1, however it may sound. You split the daddy at the position, you split the mommy at the position, and you cross over. You take a new, you generate a new chromosome that has the same length. So this is not pure, this random, but it allows you to perceive a program as if it were embedded in sort of space of all possible executions or evaluations of this program. And I think this is also similar in the natural language as we speak, because we can say, okay, there's this trait of referential transparency, and you can replace expression with its value, but it's not always the case in the natural language, because, for instance, if I say a man met a woman in the town, then a man and a woman may mean different things in different circumstances. And I think this is similar. Okay, so I've been trying to show you the pros of scheme, but it's also had some criticism. First of all, people complain that it has lots of irritating superfluous parentheses because it is a Lisp. Well, actually, I think that this is not a problem, it is rather a misunderstanding. I mean, you could easily try to imagine an editor, a program that would facilitate managing those parentheses and even do a nice typesetting for you so that the type errors would be even less probable or easier to detect than in the case of programming languages with more complex syntax. Phil Wadler wrote a paper, Why Calculating is Better Than Scheming, and it's actually the only criticism that I found. And he claimed that it has no pattern matching, and it has unfamiliar syntax, and it has no types, and no lazy evaluation. And in his criticism, because he was an advocate for using Miranda, which was a predecessor of Haskell. And he claimed that it's good to have a language with rich syntax because parsing is interesting issue on its own. But I think schemers do not share this view. I think that schemers rather claim that parsing, writing parsers like generative grammar, things like that, these are just a waste of time from the perspective of programming or of expressing thoughts, because they ultimately make it more difficult to understand a program than to ease. You have to remember the priority of operators, for example. The problem with the scheme is that it has a very ungooglable name. If you type in programming scheme, it's not, well, maybe you will get some results. It has no, well, it's not true that it has no libraries. It has some libraries, but since there's so many implementations, and for a long time there has been no common module system. So these libraries weren't portable, and also the implementations of Scheme, they often provide some extensions that are not compatible with one another. And another thing is that the reports on the Scheme were rather short, rather thin documents, but it changed with the sixth edition or sixth revision of the document, which was really lengthy, and the community didn't actually like it. And this is a quote that describes the Scheme, the view on Scheme from the newcomer's perspective. Why is it so that you consider the R5RS the last true Scheme? Is it a particular feature set, a limit on a page count, utter minimalism to the point of being virtually useless without implementation-dependent extensions? What? It seems to me that many schemers have some ideal in their minds about what Scheme really is, but that language is imaginary, existing only in the R5RS document. And the response itself can be found in the R5RS document. Scheme would still be useful as a notation for expressing computational methods, even in the absence of mechanical implementations, because essentially we do not need computers to communicate with ourselves. Maybe not now it isn't so obvious as it was in the 90s. And now some most important books. It's Abelson and Sussman's Structure and Interpretation of Computer Programs, Daniel Friedman and Mitchell One's Essentials of Programming Languages. Oh, this very important book, and it's, as I said before, it is available on the Creative Commons license. I'm not sure if it's free, Essentials of Programming Languages, but if you are interested in the theory of programming languages, it is a must-read. How to Design Programs. It was a base of a course on Coursera, Introduction to the Systematic Program Design. Maybe it's still available, I'm not sure. And there are books by Daniel Friedman called Little Books, Little Schemer, Seasoned Schemer, Reasoned Schemer, and recently published Little Prover. The last one is particularly interesting because it deals with proving properties about programs. And another unimportant book is the one that I wrote recently. You might be interested to check it out. I called it A Pamphlet Against R. By the way, R is a programming language, and Julia, you might have heard of Julia. These are numerical languages that were built on top of Scheme originally. And I will finish with an advertisement. If you have an important business client, or that you want to hang out with to make a business relation, or if you want to I don't know, like make a team integration of your team or just relax, then my brother runs an escape room. I mean, he calls it Engage Room. It is called Room of Plenty, and it is located near the Mercure Hotel and the Madison shopping mall. And that's it. That will be it. If there are any questions, I think this is the best time for asking them. Yes?
So, if the scheme is so minimalistic in its course index, why is there a lot of different versions of this language, and they can't come to one structure?
Well, because Scheme it doesn't describe what a computer should do to perform a certain computation. It only describes what is the meaning of certain expressions, for example. So implementators have a lot of freedom to decide what would be best choices on certain architectures. So obviously you've got Scheme implementation running in JavaScript in the browser, and you couldn't implement it like by compiling it to assembly. You've got some really good implementations that do compile to assembly, but to some particular instruction sets of particular machines. And similarly, there's Scheme version running in the JVM. It requires a JVM to run, and another reason for scheming, for being so many implementations of Scheme, is that there are it is easy to implement because it has so many rules. So many hobbyists just try to learn new concepts by implementing their own interpreters and compilers.
I mean, it's just about compiling to the basically either to some concrete architecture or something, but it's not related to grammar of the language. But you mentioned that there are libraries, and there are not so many libraries, because actually one library written in one dialect of this language sometimes is not working on another dialect. But this is not possible in case the grammar is the same.
No. I think because there are two things here. First, the module system. The specification of Scheme, R5 revised, the fifth specification of Scheme didn't define any module system. So there was no commonly accepted way for defining modules, and every author of a serious implementation came up with his own interface to the module system. And some Scheme implementations provide extensions. For example, if you have this Kava Scheme, it runs on the JVM, and it gives you the functions from the JVM, and it gives you special notation that doesn't work in other implementations. Okay, any other? Oh, yes?
How often do you use it in production, and what kinds of projects?
Well, I think it depends on the kind of production, but
yeah, just wonder what kinds of projects are good for Scheme.
Sorry, I'm a philosopher, so I don't know, but I myself have been writing a computer game, and it's in a 3D environment in Scheme, and I've heard that it was used to write scripts while they were making Final Fantasy, the movie, I think the Japanese were using it, and I think Scheme is also popular in Japan. But what are the practical applications? I don't know. Maybe these are just well-kept secrets. Any other questions? Okay, yes.
Is it really a pro for you that minimalism is giving you right to express the very essential parts of any programming, like pattern matching and stuff, by yourself instead of having it out of the box?
I mean,
because many minimalistic things, many essential things that should be actually in kind of programming language, just should be there. You should not, you should have ability to express something through macros or another stuff, but this, come on, you should not redesign every time your if.
Yeah.
Because you just want to code, so I will have my GitHub repository where I contain my if pattern matching and stuff.
Yeah. I mean that's absolutely true. But on the other hand, I think that the most programming languages, that they make some decisions for you. They give you their idea of how to express programs. And in the case of Scheme, you can you've got this minimalistic set of rules, and you can expand it. But of course, I agree that this is problematic. That for instance, if everyone had their own pattern matching library, it would be and they weren't compatible with one another, then it would be actually an obstacle in communication. But I also think that Scheme is in a large part a culture of discussion, of trying to come up with a best solution, and I think it encourages this trying new different solutions, or when you finally come up with a solution that you think is good enough, then maybe people will pick it and use it.
Yes, but you can't always trust a particular solution. When I use some pattern matching, for example, in Java, I trust it's working. It was tested. But if I have to write it by myself, I'm not so sure I didn't make any mistake. There is not something I didn't talk about. And I'm not sure it will work in every condition. So you said the scheme encourages to discuss ideas and build better solutions, okay? But if you don't have official repo that everyone uses, and still everyone uses their own implementation of pattern matching or everything else, everyone uses something that
I agree.
It will work in production.
Yes, I mean, and other thing is that you get a mess. Instead of simplicity, you get this more complication. But I think I don't think that it has ever been a problem in practice. Maybe because nobody uses Scheme in practice. But as I said before, I perceive Scheme in large part as a way of just of expressing ideas, and the code is intended to be read, maybe is intended to be reasoned about. Maybe you can be more sure when you are also able to write a proof of your implementation that it works. And I think it is much easier to do that for a Scheme program than for a Java program. Okay. Any other questions? So, thank you very much.
Dziękuję bardzo
Dzięki.
za wystąpienie.